Hello, this is Josiah Winslow recording for his Programming in Java course at MATC for instructor Mark Cribb. Now this is actually the second part of my final project in Java. The first one had to do with making an Alexa app, or an Alexa skill, which I don't know what that has to do with Java because we use JavaScript, but in any event, you can see the video for that in the upper right hand corner right about now. So this is the video where I actually showcase my final project in Java, and there are a few requirements that we had to meet. So we had to do file reading/writing, classes, methods, arrays and or array lists, and finally recursion. Now, I decided that the simplest way that I was going to meet all of those requirements was make a programming language, and then write its interpreter in Java. So let me show you what I mean. I actually made an entire website for it as well, because this was a final project for another one of my classes. And if you want to visit it, I've linked it in the description below, and it explains basically everything you need to know about it. So I won't be explaining how the actual language works in this video, but I am going to explain as much of how the interpreter works as I can. So let's get started on that. So right here I'm in NetBeans, and as you can see right here, this is all of my source files for this program. And how many is that? That's 6, 7, 8, 13, 18, 19, 20, 34 source files. My gosh. This is a lot, but I made it work. So I actually even used a library as well called Apache Commons CLI for command line parsing. So just really quickly, I'm going to come up here to the project configuration. And then here you see this is meant to be run on the command line with a certain set of arguments, but I have to supply these here because I'm not exactly on a command line right now, I'm in an IDE. So first I am going to go through how the interpreter works, and then I'm going to showcase it running. So at a very high level, first, we have to define command line options. I have two of them right now. The quote-unquote optimization level from 0 to 3, which basically a higher optimization level means the code runs faster at the expense of it being not as accurate to the specs. And finally, there's the H option, which just displays a help message. So I have to parse the options, and if I chose the help option, if I chose to include the help option, I print the help message. Otherwise, I keep going. So the default optimization level is 0, no optimization, and then I parse that value and check if it's within the range of 0 to I defined 3, and if it's not, I throw an error. Otherwise, I keep going, and I store that into the optimization level. So right here is the reader that actually reads from the file, and I will get the actual file name from the command line arguments, and then I create the reader right here, the file reader that's going to go through the file. And then, once I have that reader, what I do is I pass it to the lexer, and I'll explain what that is. I pass the lexer to the parser, I pass the parser to the interpreter, and I also pass the optimization level, so it can run it at the specified optimization level. And then I call the interpreter's execute method. And I wrap this all in a try-catch block because I don't know how to handle errors other than to report them to the user. Because if it's at this level, then there's something wrong with the code that you wrote in my language. Not with me. So, at a very high level, what a lexer is, or sometimes it's called a tokenizer, is it takes some sort of sentence or group of sentences, and basically it says, what words am I seeing? And then the parser takes those words and says, okay, how are these sentences, or how are these words fitting together to form this sentence, or this paragraph? And then the interpreter is basically, okay, so now I see these sentences, I see this paragraph, what does it mean? What am I supposed to do with this? That is, at a very high level, how it works. And I mentioned tokens. Tokens are their own type. They each have a type and a value. And the token type is one big enum that defines names for each of the values and values for each of the values, as well as a property that I am calling reserved. So if this is like a reserved keyword, like this is actually a set of alphanumeric characters that represent something special in the language. So yeah, simple setter. I only have a setter in the constructor. You can't just change these, but I do have getters. And all of these tokens are basically what the lexer tries to turn the file into. And I also have this type called value, which is an abstract class with a generic type. Now this type can be any type. And I have a simple setter and getter for it. And there are three extensions of value that I have. Bool value, which stores a Boolean value, and it's basically the same. And I also have this equals method, by the way, to check for equality between values. If they are of the same type and they hold the same value, they're equal. That's it. That's all this is. And I also have the same for a num value, which stores a big integer, and a string value, which stores a string. And finally, the final type that I want to get into before I look at the lexer, parser, and interpreter is AST. It is an abstract class that defines what is called the abstract syntax tree. So, an abstract syntax tree is basically a tree, the programming data structure tree, and it has certain values at its nodes that basically interpreting a program is walking down this tree of nodes, and that the parser turns the words that it sees into that tree. And I have a whole bunch of different types of nodes. For example, bool nodes. I have bool, num, and stir, and each of those are nodes that represent bool values, num values, and stir values respectively. And there are like a few different main types of ASTs, and that is expressional AST, which represents some expression that is to be evaluated and given a value. Operational AST, which represents, it's actually a subclass of expressional AST, and operational AST is specifically some operation that is being done on some different values, or some different expressional ASTs. I also have statemental ASTs, which there are two different kinds of statements right here that are in the language. And statemental AST is either one of those. And then finally I have a valuational AST, which is itself a kind of expressional AST, which specifically holds a value. And that's what the bool, num, and stir were over here. What am I forgetting? Oh yeah, there's also structural AST, which a structural AST is very basically just, it has to do with the structure of the program itself. For example, program is a structural AST. The entire just root node of the tree itself is a structural AST, and a line is a structural AST. Perfect. Now with that background out of the way, I can get to explaining the lexer, the parser, and the interpreter. So I use a pushback reader to read single characters at a time from the file stream, or file reader stream, and also it's a pushback reader because I also need to peek at the next character sometimes without actually reading it. And a pushback reader lets me do that. It has a command for reading one character from a stream, and it also has a method for unreading a character from a stream. And what it is it just pushes that character back onto the stream such that once it's read again, it'll read that same thing. So this lexer's internal state we have a pushback reader up here. We have a character which represents a current character. Now this is a character instead of a char because I also want it to be nullable. Because, you know, sometimes there might not be a current character. There's just nothing. We've hit the end of the file. And finally, we also have a hash map from string to token type, which it converts a string back to a token type because I don't really have a way to, you know, turn a string into a token that represents that string. This is what I do. And finally, I have a boolean done reading, which if it is false, then we still have more characters to read, and if it's true, we don't. So right here, the state is initialized, we advance one character, and we make the hash map of the token types. Now the advance function, there are two functions that I use for going through and parsing these characters. And they are advance and peek. Advance basically reads the next thing from the reader, and then if we have reached the end, then we stop. Otherwise, we store the next character as our current character. After casting it, of course. And we also have a peek function, which reads the next character, and if it's done, we're done. But otherwise, it takes that character we just read, unreads it, and then returns it. You know, so it's like peeking forward one character into the stream. And I do that because I need it sometimes. So we have all these functions I'm going to get to. So the main function that the only public function in the lexer is one that gets the next token. And the parser uses this as it's going through the tokens. So the main loop here is while current character is not equal to null. So while the character that we have is still within the actual stream that we're reading. So if space, tab, or carriage return is the current character, we skip it until we see a character that's not one of those. And that's all we do right here. While current character is not equal to null, and basically current character is not in any one of these, or no, while it is one of these, advance. And it keeps advancing until it hits a non-white space character. Here, pretty much the same thing, but with comments. So if current character is equal to slash, and peak one character forward is equal to slash, advance over those slashes, then skip the rest of the comment until we see a new line, I believe. Yeah. Keep looping while current character is not new line. Alright, and next we have if the current character is within this string. I didn't use isDigit because I don't accept all Unicode digits, but isDigit is a function of the character class, I believe. And it does this, but it also accepts more, and I didn't want to. So if current character is in this string, then the next token we return is a number. And then let's go up to that function to see how it gets it. So here we have a string builder, and it's going through, and while we are still building the number, we append the current character to the string builder, advance one, and then we create a new token that's of type number, and it has the value of this num value, which we create a big integer with the stringification of the string builder. Alright, pretty simple stuff. If character is alphabetic, so if it's some letter of the alphabet, then it's some word, some sort of like keyword in the language. So we return word, which we've defined up here. So again, we use the string builder to get the current word. And if token types does not contain that key, then I throw an exception saying a token for this word was not found. And furthermore, this has to be a reserved token because, for example, the values of the token types number, boolean, string, and EOF are just those literal values. So we have to not have it match on those. Those are not their tokens. Those words are not their tokens. So if the token type is not reserved, we throw an error. Otherwise, we have some sort of token. And I actually have to put this in some sort of a switch statement. So as you can see right here, if the token that we found is the one with the value true, then we have to turn it into a token of type boolean with the value of true, or a bool value of true. And same thing with false. We turned it into a token of type boolean with a bool value of false. Otherwise, it is a token with that token type and with no value. Alright, so we're still going through trying to get the next token. If the current character is equal to the double quote character, then we advance over it, and then we return the rest of the string. So let's go up here. And we're getting the string. We're going through building the string builder right here. Now, there are a few caveats to this. If the current character, when we go through this loop, if the current character is a backslash, we are parsing an escape sequence. And an escape sequence is basically like backslash n, backslash r, backslash t, those kinds of things. We've used them in class before, and here I have to parse them myself. And there are a few escape codes. There's backslash a, which I think stands for alert, or like a bell. B stands for backslash. Form feed, new line, carriage return, horizontal tab, vertical tab. This represents, one slash right here, but this will be for just like a literal backslash. And then finally, backslash quote will stand for a literal quote. So if the current character is this, then we advance over it. We try to find out what the next character is, and if it is an escape sequence, we add the relevant character. Otherwise, we add the relevant character from the escape sequence. Otherwise, we just have it be the raw character. So like \C does not correspond to an escape sequence that I've defined. So \C in a string is just going to be parsed as C, the literal character. That's it. And if a return if a carriage return or a new line is within the string, that's illegal. We throw an exception. And if none of that was tripped up, then we just have a literal next character of the string that we add to the string builder. And then we advance over the next character. So we keep going, and then we keep going until we hit a quote character. Then we advance over it, return a new token that's of the type string with that stir value. Alright, so if we haven't been tripped up so far, then we might be looking at a two-character string. Or not a two-character string, two-character token. There are quite a few two-character tokens, like less than or equals to, the or, the not, or no, not the not, but the not equal to. You know, we've got a few of them in here. So if peak is not null, then we try to get the token that corresponds to that string. And if we have it, yippee, that's our new token. We advance over it, and then we return that as a new token. Otherwise, we have some sort of one-character token. So if we have that, great, that's our new token. Advance over it, return that as a token. Now, if at this point we have not found a token in whatever we're trying to parse, then we don't have a token, and there is some sort of syntax error. Or not syntax error, but whatever you call an error where you don't even have words in the first place. I think that actually is a syntax error. But anyways, you throw an exception, and once we are done parsing all the tokens, then if we ever need to call this again, it just returns EOF, which stands for end of file. It returns that as a token. Alright, so we take that lexer right there, and we give it to the parser, and then the parser controls how fast it goes, or when it goes, or what it reads. So right here, as a state, it has lexer, and it has current token. So we set the lexer to lexer in the constructor, and we eat a token. So now something is our current token. So right here, private token get next token just calls the lexer's get next token function, and so does this, the eat function right here. And I've actually overloaded this with another function, and I also have a separate function called eat choice, which, to be honest, I probably could have overloaded eat with it, but I wanted to make it a little clearer to myself what it was for, so I called it eat choice. And eat gets the next token and has no problems. Eat with a token type eats the next token, but like if it's not a certain type, then it errors. And same thing for eat choice, except we are given a variable number of arguments, and it checks each of those to see if the current token is indeed one of those choices, then yeah, we're okay. But if it's not, then we error. Alright, so the public parse right here returns program. And I've defined a few different syntax elements each of which are represented by ASTs, starting up here with program. So we have a list of ASTs that goes in the program, and these are all the lines. I would have made a list of lines, but I made a list of ASTs instead because I wanted it to be a little more general. That's within the definition of... was that the... Yeah, that's within the definition of structural AST, is a general list of ASTs. So we have this, and then we keep eating new line tokens. We keep consuming new line tokens until we get to some line that is not empty. And then while current token.getType is not equal to token-type.eof, so while we haven't hit the end of the file, we add to our lines list a line, which we'll explain in a bit. And then we keep going past new lines until we get to the next line, and so on and so on and so forth until we've hit the end of the file. And then finally, we return that as a program. So the line right here, lines consist of line numbers, some number of conditional statements, and some number of statements. So here we define the line number node as a num node, and we're getting line number from our parser, and then we are converting that to a big integer right here, and that's going to be for the new line constructor. And here we have a list of expressional ASTs that each correspond to each of the different conditional statements that could be before this actual line, which affect when the line runs. So while the current token type is of either again, defer, and forget, it keeps eating that, then a left parenthesis, an expression, and then it takes that expression and adds it to the corresponding list, eats a right parenthesis, and it keeps going. And then finally, we have an action, which is a list of statements. A list of ASTs, anyways. And then after that, there should be a semicolon, and then either a new line or the end of the file. Then we return the new line. And next we have line number, which gets the value of the next token or current token as a num value. And if it's line 0 is illegal. I cannot have a line 0. Otherwise, I eat it as a number, and then I return that. Alright, so an action right here is a list of statements. So I define the list, I add the first statement to the list, and then while the next token type equals comma, I eat a comma and add another statement, then return statements. And right here, there are two types of statements. Ones that start with print, which will be statement prints, and ones that don't, which will be statement push. So a statement push, it consists of some expression, maybe a hashtag, and maybe another number. So it pushes. So right here, we gather the left side with an expression, and the right side I have set to null, but if current token.getType equals token-type.hash, I eat the hash, and then I eat an expression that I see on the right side, and then that's the new statement. So push statements can be either single expressions that say push one copy of this onto the program's to-do list. Or they can be multi-push statements. So there's an expression, hashtag, and then another expression saying how many times to push that line number onto the list. And as a reminder, both of them can be negative, though that will mean something different. So here we have a statement print. It consists of the word print, a left parenthesis, some list of, and here we're defining some parameters that if current token is not a right parenthesis, so if we haven't just like immediately passed nothing to print, then we add a expression or a string. That's what string expr is. It's just like a choice between a string or a string or some numerical expression. And then I keep adding params while I see a comma in front of me. Then I eat a final right parenthesis to end the print statement. Return that as a statement. So here the string just eats a string and returns it as a stir node. And string expr, if it sees a string in front of it, it returns the string. Otherwise, it returns a numerical expression. And the numerical expression, this is a very complicated way to set it up, but basically, I'm calling all of these different functions for different types of expressions, and I'm not gonna go over them, but I'm not gonna go over them all, but each of them are basically defining, here's what different statements look like, and if it's not this kind of statement, then it's some other kind of statement. And see, here's where most of here's where like the big pile of stuff stops. And then I switch on token type and say if I see these, then I do all these. But otherwise, if I don't see any of those, then it's a token that does not belong here in a numerical expression. And then finally, also at the bottom, I have a function call. And whatever it is we eat the name of the function, a left parenthesis, we gather parameters as before, eat a right parenthesis, and return that as a function AST. So here it's a function. Alright, and last but not least, we're going to get to the interpreter, which actually does not just consist of an interpreter, but I'm going to go ahead and explain these classes. So this is an environment. It just has some input stream and two output streams, just like system. There's system.in, system.out, system.error, and this is just like that. And if you call this constructor without arguments, then it just defaults to system, using what system has. And you can pass some environment to the interpreter, and that's where we'll get its input and output its output. And here we have a to-do item, which has a node, which is some line. So like each item on the to-do list is a line on the program. So we have a line, and we have a count, which is how many times this line is supposed to be on the list. And here we have simple getters, and we also have this setter right here that's change count, which it will change by this amount, and it will return however many extra that was left over. Like if there are like 5 copies of something on the list and you try to remove 7, that's 2 left over. Like it'll just be like you won't have any copies, but like you'll have removed 2 extra. So it returns the 2 that is the extra if it's that case. Otherwise, it returns a 0, and then it adds the change to the count. now we have a to-do list, which it even has a randomizer, because it is gathering its own, like, it has to choose a random line from itself. So this is how I chose to do it. So the list itself is a hash map between numbers and to-do items. Now, I don't actually work with the big integers themselves because I've been told that it's really bad to have them as keys to a hash map. So instead, I'm using their hash codes, and I also have another thing mapping from a big integer's hash code to a big integer because I saw no other way to reverse it. So that's how I've implemented that. I also have big integers representing the total amount of lines on the list, which is a little bit of a redundant way to quickly check how many lines are still on the list. We could just loop through and do the count, but why? It's slow. We also have total no-ops and total defers, as well as nops and defers. So nops are lines that are no operations, they do nothing. And I use those in certain optimization levels. And defers is same thing as lines that we have just deferred. We have, chosen them for execution, but for whatever reason, we're not ready yet. So we have some initializations. We have to make sure that there are no duplicate lines on the list. And here we have a getter for get total to do. Here we have a getter for getting a line from the list, and we have to pass a line number, and we try to get it from the list by its hash code. And here we have get line count, which does not get a line itself, but rather gets how many times it appears on the list. We have some functions for marking that we have just deferred a line, unmarking that we have deferred any of the lines, and marking a line as a no-op, which there's a section of the interpreter that checks for this. And here we have a function for getting a random big integer within the range 0 to whatever end is right here, inclusive. And the reason I define this here is because there is no function for this in big integer. So I just literally keep repeating generating a big integer of the appropriate size. And we have to do this until we have to do this until the result is less than the endpoint. Then we return it. So finally, whoa, what happened? Okay. So finally, we have get random line, or not finally, but here we have to generate a number from the range of 0 to however many lines that we can choose. So that's going to be the total to do, but we're not going to take into account the deferred lines and no-op lines. And if the range is empty, return null. There's no line that fits. Now we get a random big integer, and then we go through and we iterate through each entry of the list. So if we have just deferred it, then we're not going to defer it again, and we continue. Otherwise, if it's a no-op, we are also not going to choose it. We're going to continue. And if the item.getNode is nop, which means if the list item has been marked as a nop, but it's not within our list of nops in the to-do list right here, we mark it as a nop. And if line to do dot compare to item dot get count is less than 0, which, what does this do again? Oh yeah, so if whatever number we have is less than however many copies of that line are on the list, then we're just going to choose that, and we're going to return it as a big int, or as a big integer. Otherwise, we're going to subtract however many that is from the line to do, and then we're going to get some other line. This is the most fair way that I've found to choose a line at random. And also, this exception should never execute, but, you know, you never know. And finally, we have change count, which is basically like change count for the individual items, except that it takes a line number and however many copies. So if you try to push a positive amount of a negative line, then it's like pushing the negative amount of that positive line. So that's what this is. And then we also take into account whether or not this line has just been deferred, or if the line is a no-op, and then we adjust our count of the total to do and the total defers and total nops in the same way. Alright, we are almost through explaining everything about this. So here we have a node visitor, and I have two classes that extend from this. They are the evaluator, which evaluates numerical expressions, and the interpreter itself, which runs lines. Each of them have one thing in common: they visit nodes on an abstract syntax tree. So here we have just like a generic return type visit, and what I actually do is I have it run the function that I've defined with a certain name, visit, and then like the name of the actual node. And I tried to get it and then invoke it using the context of the node visitor itself. Otherwise, I return a generic visit. That is, like, if it can't find a function to visit, it visits this, and it throws an exception. And my IDE yelled at me if I did not include this, so I include this. Alright, perfect. So now, the evaluator and the interpreter. So the evaluator evaluates numbers, or numerical expressions, and as you can see, it takes in a to-do list as input, because sometimes the values depend on what is on the to-do list. There's one function n that takes a numerical argument, and it returns the amount of times that the line with that number is on the list. We have an environment because we have a function called read that needs to take input as an integer. Optimization level, current line, because sometimes we have to deal with that in expression parsing. And then finally, a scanner, which turns the lines that we read from input into big ints, or big integers. So here we have evaluate, which, if we are not evaluating the expression, then we throw an exception. Otherwise, we create an expressional AST of it. We have to, because I made the visit function generic, we have to cast it to an expression. And now, if this is the first time the optimization level is relevant, if the optimization level is greater than or equal to 1, so if the level is 1 or above, then if we have stored a simplified value for this, then we just return it without even evaluating. And that's what I do if the level is 1 or above, is every time I evaluate an expression and I'm sure it's going to be constant, I store it as some key, some property on the expression AST. So the current line is the line, and then we return the result of visiting this expression node. So this function, as Boolean, takes a value and tries to convert it to Boolean. So if it is a Boolean, no problem. If it's a string, problem. But if it's a number, then if we try to convert a number to a Boolean, then what happens is the result is true if there is more than, if there's one or more copies of that line on the list, and it's false otherwise if there's no copies. And you'll notice also this means that negative values and 0 will always return false, because that's just how I made things work. So try simplifying as Boolean is basically the same thing, except it also tries to simplify the expression in such a way that instead of the numerical expression, the Boolean is stored as the simplified value. So there's a few more things I have to keep track of there. Here we have a function called error on Boolean, which takes a number of values, and if any of them are instances of bool value, then it errors. Alright. Back is killing me. So right here we have visit, which I actually, now that I think of it, maybe there's no need for this to be here, but in any event, if the optimization level is 1 or greater, then if the value exists, if the simple value exists, then just return it and don't evaluate it. Otherwise, visit the nodes. And then here we have visit num, visit stir, visit bool, which basically result in the value of the num, stir, or bool. Visit operation. There are two types of operations that I've defined. Unary, which take 1 argument. Binary, which take 2 arguments. Otherwise, exception. So there are a few unary operations that I've defined. So first off, none of them work on strings. Some of them work on booleans. So I have to keep track of that. I also keep track of whether or not this thing can simplify, and I do this for every one of these. Basically, if there's nothing that can vary with construction of the program or user input, or anything like that, then like if there's nothing that is going to change it ever whenever we evaluate it, then simplifies is true. Otherwise, it's false. Then I do a switch on the operation type, which are tokens, and if it's not, then I do a boolean not on it. If it's a minus, I do a unary minus on it, which is basically like making it negative. And it doesn't work on booleans, which is why I have error on boolean there. And if it's none of those, it doesn't work. And if optimization level is 1 or greater, then if it simplifies, it stores the simplified value. Same deal with binary, although there are more of them and it's a little more complicated. So here we have plus, minus, multiply, integer divide, mod, less than, greater than, less than or equal to, greater than or equal to, equal, not equal, and or. And they do basically what you'd expect. And same simplifying thing here. And function. I have a few different kinds of functions. Nfunc, which is basically just a capital N. Yeah, this is how you call it. And it takes 1 argument, which is some number, and it tries to see if that value on the to-do list, if that line exists. Sorry. No, it doesn't do existence. It actually returns how many copies of the line are on the list. So it's even more powerful. And here I have a ufunc, which also takes an argument, and then it returns the character with that Unicode value. And finally, I have a read function, which takes no arguments, and it results in whatever big integer is inputted on the next line. Otherwise, unsupported operation exception. Alright, now we can get to how the interpreter actually works. So, it has a program, which is a program node on the AST, an environment, an optimization level, a to-do list, an evaluator, which takes some of these, and a current line. And I, for kicks, I also made some other constructors. So, executing the actual file, the actual program, which is what we do right here. Basically, while there are still lines to do, execute one step. And executing one step involves getting a random line, and if that random line is null, if it doesn't, if get random line failed, we return. Otherwise, we visit that node. So, I'm not going to explain this check NOP line because it's rather complicated, but it's not even that sophisticated. So, there are two kinds of lines that do nothing that I check for. There are lines that are just pushing one copy of itself and doing nothing else. Or there are lines where defer is always true, if they are always skipped by the conditional statement. So that's that. And here I modify the generic visit a bit. I don't define the methods for visiting expressional ASTs in the interpreter. Instead, they are sent to the evaluator if we find them. But if they're not even there, then I return the generic visit. So visiting a line. So I take the current line. If the optimization level is 3 or greater, I check whether it's a no-op, and if it is, I mark it. And then I take all of the nodes that are the expressions within the defer statements, and then I evaluate them, and if any of them are true, then I just skip them. If it's true, I defer them for later. And as you can see right here, if optimization level is 2 or greater, then I mark deferred lines, just like I said earlier, and if I find a line that I don't defer, I unmark all of them. Then I evaluate all the forget expressions, and if any of them are true, then afterwards... Hang on, what do I actually do? Okay, so if any of the forget statements are true, forget line right here, which is initially false, is set to true. And if forget line is false, then, yeah. So if we do forget the line, then we just take one copy of it off the list and we don't execute any of the statements on it. Otherwise, if we're not forgetting it, we execute the statement, and we also evaluate the again expressions to check if any of them are true, and if any of them are true, then no copies of the line are taken off at all. And then after that, a copy is taken off if we're supposed to. And then these are the last two functions that we have to go over before I actually run some programs as examples. So here we have visit statement push, and a push statement again just takes however many lines and then pushes however many copies onto the list. And finally, visit statement print takes some amount of parameters, and then it evaluates them, prints them out, and then flushes the output display. Alright, so that is all of the expressions, and in just a little while I'm going to demonstrate some programs that are actually running through this interpreter. If I can pause. Okay, I couldn't figure it out at first, but I eventually figured it out. So, right now, I've showed you the program. Now let's show the actual programs that the program will interpret. So, right here I have to define where on my computer this is stored. I've actually stored this in a folder called Python because it's, you know, I did the first version of this in Python. So right here on the website, you can see I have a few different example programs. One that prints Hello World, one that is supposed to print heads or tails, and it'll only print one of them. Another one called the Truth Machine. Here we have one called 99 Bottles of Beer, which prints 99 bottles of beer on the wall, the whole song. You can look it up. Here's one that'll calculate Fibonacci numbers, however many you, well, the one on the website calculates only 100, but the one that I have local on my machine, it asks for a number and then it calculates that many Fibonacci numbers. And then finally I have one that calculates pi for the heck of it. Alright. So do we have that? Yep. Alright, so first let's run the Hello World program, and with any luck, this should print Hello World. So give it a sec to bring the thing up. There we are. And it doesn't print a new line at the end, so that's why the text is right next to that like that. But that's good. And if we keep running this, by the way, it'll keep outputting Hello World. And that's actually pretty amazing because the execution order is random. So that's what the defer command is for. If you saw earlier in the source code, that defers the second line, which prints world, until the first line has been executed. And so let's go ahead and do a coin flip. Actually, you know what? Let's go ahead and add the help option so we can quickly see the help file, or help instructions. Yeah, so this is how to use it, and these are what the arguments do. So let's go ahead and do the coin flip now. So this should print either heads or tails. Heads. And we can keep printing it, and now it runs tails, tails, heads, and it'll do heads or tails like 50% of the time each. And then next is Truth Machine. I believe I put a dash in it. And Truth Machine, what a Truth Machine does is it's a very simple type of program, which if you input a 0, then it outputs 1 0 and terminates. If you input a 1, or in my case, any other number, it outputs infinitely many 1s. Yeah, okay, so this is, I didn't put a dash in it. In fact, I think I just named it truth.text. Yeah, so now it's prompting for input, and if I give it gibberish or something that it cannot parse as a number, then it just keeps asking. Otherwise, if I give it a number, then it'll take in the number, and here I input a 0, so it's 1, 0. And let's input a 1. And as you can see, I have to stop this now. This is printing a large number of 1s. And it only stopped because I stopped it. Alright, so the next program we're going to run is 99 bottles of beer on the wall, which will print the lyrics of that classic song that every programmer should know by the time that they have gotten into a class like this. Oh, so there you see, it's chugging along right there. 99 bottles of beer on the wall, 99 bottles of beer. Take one down and pass it around. 98 bottles of beer on the wall. 98 bottles of beer on the... and so on and so forth. And so now let's do Fibonacci. So we're going to ask to output how many? 20 different Fibonacci numbers. And as you can see, it outputted the first 20 Fibonacci numbers. Now, if we ask it to do a larger amount, like let's say 100 even, it's going to take much longer. And that is because of the way that I have to store numbers. So I actually store these numbers using the different amounts of each line on the to-do list. So how fast it runs, and by the way, each of the lines that I have storing the last two numbers of the Fibonacci sequence, they don't do anything except in specific situations. You can only run them sometimes, and other times they just make the program stall. So as you can see, it's taken a pretty long time to calculate because it's taken a pretty long time to randomly generate the right line to execute. But that's what the optimization levels are for. And I'm not going to demonstrate all of them. I'm just going to demonstrate the highest level of optimization. And let's go ahead and output 100. And would you look at that? It was done almost instantly. And I can even do a much higher number, like 10,000. Line's too long. But yeah, as you can see, it's going pretty fast. And then finally, the last program that I'm going to run before I stop this very, very long video is the one that calculates pi. Not going to explain how it works because that would take way too long, but as you can see, if you... Oh, okay, I misspelled the file name. But if you run it... Okay, I don't know what's happening. Okay, what actually is happening? Something's up. Oh. Okay, so for whatever reason it didn't output until I stopped it, but there you go. Starts with 3.1415 and quickly devolves from there. Alright, so that is all. That is the last thing I have to show you today. So with that, I'm sorry for how long this video took, and take care.